Welcome, ladies and gentlemen, to this presentation in the course Industrial Process Engineering. This is the fourth lecture about the fundamentals of industrial robotics. Multi-purpose solutions for advanced production systems. This lecture discusses opportunities and limitations of industrial robots as solutions to provide high productivity, quality, and adaptability at minimal cost for modern manufacturing environments. My name is Nicholas Tyson and I'm a PhD student at the Department for Production Engineering under the supervision of Andreas Arkendi. Intended learning outcomes. Today's lecture aims to acquire the knowledge to understand, assess, and justify the opportunities and limitations of industrial robots as potential solutions to challenges in manufacturing processes and environments by Number 1. Understanding the requirements and similarities between established application fields of industrial robotics in manufacturing processes. Number 2. Describing the configurations and working principles of industrial robots. Number 3. Assessing and justifying how different designs of industrial manipulators influence their performance. And finally, number 4, identifying and preventing risks associated with the operation of industrial manipulators and robotic cells. Agenda. To achieve the intended learning outcomes, the lecture is divided into 6 sections. The section Introduction discusses definitions, the history and market data to identify for which manufacturing process industrial robots have been used in the past and will be used in the future. The section Configurations, or more simply expressed, the shape of the robot, looks into which type of robot is used for which manufacturing process. The section Components outlines the most critical components of industrial manipulators, such as the drivetrain, measuring systems, and additional sensors, which might be installed to improve the accuracy. The section Performance and Operation discusses the advantages and limitations of industrial robots related to performance matrices such as speed, stiffness, and accuracy, and how these performance measures are codependent on the type of operation. In that context, the type of operation means either programming the robot on a computer or manually on the shop floor. The section Safety discusses regulations and standards for the safe operation of industrial manipulators and industrial environments, as well as practices to prevent accidents. And the last section focuses on global and the department's research activities concerning industrial robotics. There will be short breaks between each sections and questions will be asked throughout the presentation. Introduction. The videos on this slide show common usage of industrial manipulators in manufacturing processes. The video in the upper left-hand corner shows a serial articulated manipulator with 6 degrees of freedom in a welding application. The one in the upper right-hand corner shows a machine tending task. The one in the lower left-hand corner shows a research project in which machine learning is used to create a trajectory for a robotic assembly. And the one in the lower right-hand corner shows a simulation of a research project which combines inspection and metal deposition. What do all robots in those videos have in common? Their shape. They are all serial articulated manipulators. Definition. According to ISO 80C-73 Robots and Robotics Devices Vocabulary, an industrial robot is an automatically controlled, reprogrammable, multi-purpose manipulator programmable in 3 or more axes, which can be either fixed in place or mobile for use in industrial automation applications. The word reprogrammable means that it is designed so that the programmed motions or auxiliary functions can be changed without physical alteration. Multi-purpose means that the system is capable of being adapted to different applications without physical alteration. And manipulator simply means a machine in which the mechanisms usually consist of a series of segments jointed or sliding relative to one another for the purpose of grasping and or moving objects in several degrees of freedom. Figure 1 shows an articulated industrial robot as the ones that we have seen in the manufacturing processes on the beforegoing slide. Figure 2 shows a wheeled robot. Vacuuming and floor cleaning robots are the most established personal domestic service robots with around 7.5 million sold units in December 2018. Figure 3 shows biped robots. Handicap assistance robots have taken off to the anticipated degree in the past few years. In 2017, a total of 6,423 robots were sold, up from 5,313 in 2016, an increase of around 21%. Numerous national research projects in many countries concentrate on this huge future market for service robots. In contrast to the household and entertainment robots, these robots are high-tech products. Figure 4 shows a Cartesian robot, which are discussed in this lecture as machine tools. And then there are also other types of robots. As we said before, there are wheeled robots, biped robots, aerial robots, underwater robots, nano robots. And any of these can also be considered as industrial robots, because the definition, according to the International Federation of Robotics, there is only a differentiation between their application fields, which then differentiates robots into industrial robots or service robots. Industries and applications. The driving industries for the growth in industrial robotics prior to the economic recession of the year 2020, which was close to 15%, were the automotive, electronics and metalworking sectors. In the automotive industries, common applications are the welding of the body in white, machine tending, spray painting, and final assembly. A driving paradigm for the automotive industry is the higher degree of product customization. In the electronics industries, common applications are the soldering, the dispensing of glues, as well as the assembly of the final product. A driving paradigm here is the increasing demand for batteries, chips, and displays. In the metalworking industries, common applications are machine tending, material handling, as well as laser or water jet cutting. A driving paradigm for the adaptation in this sector is the potential to create more integrated manufacturing concepts, like the one in the video showing the concept of inspection and simultaneous metal deposition. Figure 5 shows the installed robots by intended application from 2011 to 2015 by the application groups defined by the International Federation of Robotics. The International Federation of Robotics Statistical Department is the primary global resource for data on robotics. Unfortunately, the quality of the service is matched by the pricing, thus I'm forced to show you an old set of data. At the same time, I have to admit that they are quite generous, as I have received this dataset for free when I was still a student. Based on more recent information, the ranking of the application groups is still valid. The most common application group is handling operations and machine tendings, and robot for that purpose can be found across all aforementioned industrial sectors. The second biggest application group is welding and soldering operations, which can be arc welding, spot welding, and laser welding. And the third biggest application group is assembling and disassembling, which ranges from the assembly of mobile phones to heavy-duty trucks and yachts. International Industrial Robotics Market. Figure 6 shows the annual shipment of industrial robots in thousands on the left-hand y-axis and the cumulative installed units on the right-hand y-axis. From 2020 to 2022, almost 2 million new units of industrial robots are expected to be installed in factories around the world. The technological trends of simplification, collaboration, and digitalization can be expected to promote the installation of industrial robots because the programming and installation of robots will become easier, human-robot collaboration gives the ability to work in tandem with humans, and industrial robots are a central component of digital and network production as used in Industry 4.0 or cyber-physical systems. A short history of industrial robotics. Figure 7 shows the first ever developed industrial robot, the Unimate, which was developed from 1954 to 1959 by George Devol and Joseph Engelberger. It weighed 2 tons and it was controlled by a program on a magnetic drum. It used hydraulic actuators and it was programmed in joint coordinates. That is, the angles of the various joints were stored during a teaching phase and replayed in operation. Much of the technology that makes robotics more human-friendly and adaptable for different applications has emerged from manufacturers of industrial robots. Industrial robots are by far the largest commercial application of robotics technology today. All the important foundations for robot control were initially developed with industrial applications in mind. These applications deserve special attention to understand the origin of the robotic science and to appreciate many unsolved problems that still prevent the wider use of robots in manufacturing. The world's first industrial robot was used on a production line at the General Motors Turnstead plant in Trenton, New Jersey, which made door and window handles, gearshift knobs, light fixtures and other hardware for automotive interiors. Obeying step-by-step commands stored on a magnetic drum, the Unimate robot's 4,000-pound arm sequenced and stacked hot pieces of die-cast metal. The robot cost around $65,000, which amounts to around $400,000 in nowadays buying power, to produce, but Unimation sold it for only $18,000 due to delays. A rule of thumb attributed to the International Federation of Robotics says that the cost for the installation of a robotic cell are about 4 times the price of the actual industrial robot. Then, taking a leap of approximately 50 years, we find that ABB's smallest ever multi-purpose industrial robot weighs just 25 kilograms and can handle a payload of 3 or 4 kilograms with a reach of 580 millimeters.